talking long, so I'm going to try to start right on time. And I know some people will come in late, and everything is videoed, so you guys can catch something if you didn't get it. I just want to make sure I get my full 50 minutes. I thought I'd take more usually. Did everybody get to this page? Yes? So I asked you guys to do two things. One was to register for the Google group. I think I saw everybody there. If you haven't done it, please do so. There you would have found a link that got you here, and here you'll find, I'm still probably going to completely make it prettier, but you can find slides in the video. The video actually comes under this Echo 360 system. I couldn't figure out how to give a public link. I can give a link that UTA people can use, but I want it to be public. So anyway, I download it, and then I post it back up to YouTube. That's what I'm doing. So now you have a video link here. But I'll put the raw data files actually here in the Dropbox. So you guys can, if you want the raw files for some reason, whatever, it's there. Yeah, I'll try to even put the slides for the lecture that I'm giving today up. Okay, so I think in a week or two what's going to happen is that there's a few colleagues and graduate students that I'm working with around the world that are interested in following up with the lecture. They know all the introductory material pretty well, but as we get into more of the the data sets and those type of things, they're going to be interested in getting involved. So I'm going to probably use Google Hangouts or something to bring them in. Okay, so that's that. So I want to, by the end of the class, hopefully everybody's here. I want to take a little survey of who's what major and stuff like that again, and try to start remembering you guys' name. But since everybody's not here, I'm not going to do that. Okay. So today I'm going to finish up what I was trying to do before and get started in Unix, Python, and NumPy, and those type of things. Unfortunately for some of you guys, this will be very boring because I'm going to be at a very, very basic level. But I'm doing that on purpose because, in principle, there is no prerequisites for this class. I want everything to be very, very clear. So I want to just say everything at least once. And as I said, some people are going to be way ahead of the other people. And so just bear with me a little bit today, okay? And so the goal is that I'll introduce these things, and then Monday and Wednesday I'm gone. I'm in San Diego for a meeting for software for Heidelberg LAC. And so I'll end up, so what I thought I'll do is I'm going to put together some Jupyter notebooks that will allow you to work these things out, some things to work through. And the idea really is just sit down and go through it, and if you get stuck, to be able to ask the person next to you, and I'll have somebody here. It won't be difficult stuff. It's just a matter of making sure everybody is with me when I get back on Friday, and everybody can, start doing stuff for real, because they had some time to do it, and if they got stuck, they could ask the person next to them, and they worked it out. Okay, that's the thing. So I asked you to make so the first thing was to get the account, join a Google group. I also asked you to get an account in our system. I think there was 4 accounts made, and the rest of you already were a part of the system. Then I asked you to log into the Jupyter Hub, the Jupyter notebooks, and I don't know, something happened. Grayson, who messed up something, and he's working it out. It's fine. By Monday, it should be up. And so I hope that everybody did get their account, but if you didn't, everybody did here, right? No. So that was your homework, man. Write an email to Grayson, please. Okay. So get your account. So you did it, but you didn't get your account yet? Okay.
I did it today.
Okay.
What was your name?
Ryan.
I literally just sent you an email.
Yeah, I responded back with a password.
Okay. All right. So so make sure that on Monday you can, log in. And also, please, I would say bring your laptop every single time. But all the lab sessions, please bring your laptops. Okay. Okay. So let's get started and stuff. So I'm going to finish the intro. I didn't get much time to go over the class stuff, so I just whizzed through it. So I'm just going to show it again and make sure that everything's clear, right? And then there was 3 sections that I didn't go through about that I'm going to go through, and then I'll go over this stuff. Okay, that's the plan today. So this class, so I did mention that we're going to try to do these things where we're going to have probably 2 lectures and 1 lab a week. Not every single week, but most weeks we'll try to follow that. As I said, you should sign up for the accounts. The first things are exceptions. As I said, again, office hours. I have an open door policy. We all said this stuff last time, so you guys know. set the, I flashed this up here, but the requirements for this class are, some basic knowledge of all these things, not requirements. These are requirements for doing what we need to do. But there are no prereqs for the class, so I'm going to go through the stuff at some, sufficient level of detail for you guys to understand what we're doing, but not, so much so that you're going to be like, claim that you've taken a class in the thing. Just out of curiosity, just here, how many people have taken linear algebra? Okay. And then how many people have taken some sort of probability theory class?
Does quantum count?
It helps. It does help. Yeah. Okay. All right. That's fine. Then this stuff is how you're going to see. How many of you guys have taken modern physics? The physics majors have, and some of the others. Okay, so that helps also. That stuff. All right, and then of the physics people, how many of you have never? Has everybody ever coded? You've never coded?
Fortran 77 is.
Okay. All right. So you're our test case of So I'm sort of talking to you most of the time today. And look, if you need extra help or something, or you don't understand something, come talk to me, and we'll pair you with other people, and we'll get you up to speed as soon as we can. Okay. All right. All right. So most of you probably you probably know what Unix is. Maybe you know Python is, but these things aren't familiar to you. I'll explain that today to you. Okay. The course plan, as I said, I know what I want to cover in terms of material. It probably will take me longer than what I said here to do it, but I've left a lot of room in the schedule to push out. And really, I'm going to gauge this to you guys. I don't know exactly what the level is of everybody, so this will become better over time. But if you go like this, then we have a good 6 weeks of doing projects. And I want to do 2 sets of projects, and I'm going to ask you guys, everyone, to do a presentation because that's an important skill to pick up. And then what I'm going to do is that based on the projects, and we're going to spend a week talking about the projects, different opportunities, and I want to actually talk to you guys and work out what the project would be in front of everybody. Okay? And then based on those, I know there's these topics that I need to cover for you guys to have the background for your projects. Then I'll give you guys lectures that target the things that you're going to be working on. That's in the plan. It leaves a lot of time for us to actually work in class and make some progress and do checkpointing and talk to each other and get some advice. Okay? So we're going to, the class is going to kind of change. I don't know how much time we'll have for it, but it's going to change at some point into sort of really a working class, basically. All right? All right? The grading, as I said, attendance, the 10%. If you're not going to be able to make it, just let me know. I'm recording these things, okay? So I just want to, first of all, I want to give you 10% free, but I just want to encourage you guys to come. You guys have to be here for the labs. That's the one thing, okay? For sure. The homework's 20%. As I said, I'm going to assign them as we need them. So it's basically, you guys do this because next time we're going to talk about this, so you guys, by that time, finish it. And if I give you due date, and I'll start giving you explicit due dates, it'll be 1 letter grade lower every time you come to class and you don't have your homework, okay? And I said it's okay to work with others because I expect you guys are all going to be at different levels. And I hope work for others, and I think at this level you guys are at that stage. If you're here, you're interested in this stuff. And work for others doesn't mean copying other people's homework, right? It's not that kind of class. It means someone else helps you. In fact, I might even make it such that as people are working at it, you guys can see other people's solutions. But the point is to be able to get through them yourselves. Okay? That's what I just want. Really, I'm trying to get you to spend time alone at home working on stuff, and then maybe working in groups, that kind of stuff. Not just time you're spending in this class. That's what's there. I'll give you 2 take-home exams. Those I want you to do alone. Okay? And then the projects. And the projects are like 50% of the class, so it's really working towards those projects. I already talked about this stuff. The resources, the main machine that we're going to use for everything, this is the gateway. It's called Orduin.ut.edu. So your accounts are there, so you always will go through that. It should be right. It's only accessible through SSH. You guys are running Jupyter Notebook by doing something called a tunneling for SSH. I will explain what SSH is and all that kind of stuff today, actually. And then there's the recordings, as we said. Okay. This was the homework. Let's not talk. You guys saw it. You're supposed to see it. So let's talk about. So last time I got a chance to tell you a little bit about how physicists build models, right? And I got a chance to tell you a little bit about how deep our brains work, and they're like, you know, how we build models, and how deep learning is all about building models of things, right? Now, what I want to do is start to explain to you what a high energy physics experiment actually is, and then to be able to get you an idea of what the data is going to be like. So that's what I'm going to talk about. So you start getting that in your head. A lot of these things, it takes a long time to get it sort of in your head and understand it. You need to see it many times. So I'm going to sort of present everything at a very high level, but we're going to go back to all these things and go in detail on many of these aspects, okay, as needed for what we're doing. But I just want you to sort of have a big picture of what's going on, so you're not like flying blind when we're working right now. Okay? All right, so let's start with this. And so particle physics, we're trying to look at, you know, particles are extremely small, right? So how do we see something that's really small, right? The way you're seeing stuff is that light is coming off of, you know, the light, it bounces off something and then goes into your eye. And if the light has some inherent wavelength, right? So imagine that there's a ship, and instead of seeing something where you're going to be, you're sitting on water, and all you can feel is the water going up and down. And you want to know if there's a ship in front of you or something in front of you. What you can do, just like light, you can send a wave, right? And the wave can go, and it'll bounce off that ship and come back at you. So when it comes back, you know, oh, there was a ship. That's effectively what's going on. Now, if that wave was really big, what might happen is that it won't actually go, there won't be much of it reflected, and what will go is that it's like a very big swell, and the boat will go up and then go back down, right? And you wouldn't get much of a reflection, right? So there's some characteristic wavelength that you need to be able to see something. So rule of thumb, if you want to see something of a certain size, the wavelength that you want to use to be able to probe it should be of order the same size, right? If it's bigger, you're not going to be able to see anything, right? So that's basically the idea. So that this is the idea, is the picture you want to have in your head. And this is what we do with particle physics, except here, I think it's on the next slide. Well, this is basically the same point. So this is how your eye works, right? So if your light goes, bounces off the object, the wavelength is smaller than the object, you can actually see it, okay? And if the wavelength is greater than an object, it'll just go through. And that's how radio waves work. That's why you have, you know, signals can get through the walls. It's because the wavelength of those waves are bigger than the structures in the walls. So there's another concept in physics is, so if you want to see smaller and smaller objects, you have to use smaller and smaller wavelengths. So a smaller wavelength means a higher frequency. And in physics, if it's a particle, usually a higher frequency, and what I'm talking about here is a de Broglie wavelength for you guys, like the physicists, right? Means a higher frequency means higher energy, right? So E equals H and U for you guys that did this stuff, right? So, so to see things at really small distances, we need particles that go at really, really high energies. Now, our eyes can only see certain wavelength of light, so we need special detectors to see these wavelengths. And actually, we don't have to use light, and we don't use light. We use other particles to do this. So, you know, our vision works by bouncing off light, but it doesn't have to be light. You can bounce off other things, right? And that's what we're doing. So, the one thing to realize is that all particles, when it comes to quantum mechanics, all particles have wave-like properties. So, this is sort of the wave. They call it the particle-wave duality. It's not really a duality, it's just the nature of how things are. And that, the wavelength, the natural wavelength is related to the momentum of the particle. And that's basically the de Broglie formula. Okay. Let's see. All right, so then when we try to look at an object closely, the basic question that we have in particle physics is that, so we're trying to figure out what is a constituent of matter, right? So what I want to do is break matter up into the smallest pieces. I want to have the highest resolution. So if I am, for example, looking at a proton, and a proton happens to be made out of 3 quarks. If I want to see the proton, I have a certain wavelength I can see, but if I go to a higher wavelength, then instead of interacting with the whole proton, I interact with the constituents of the proton, right? This is how the partons and the gluons, the quarks were discovered originally. Okay? And then this picture that I had messed up before, I explained to you guys that all particles are associated with fields, and the way that forces work is that if I'm an electron, and let's say there's a muon sitting there, and we both are charged, and we're going to feel each other's force, classically the way you guys would do that is just use Coulomb's law, right? My charge, that charge, 1 over r squared, some constant that tells you the force that we feel. But quantum mechanically, classically when that happens, that's instantaneous too, right? The way that the equation is written down. Especially in gravity, it's instantaneous. But when it comes to sort of the quantum mechanical level, we sort of imagine this as being sort of an exchange of particles. What happens is that the electron, they throw a photon at the muon, and the muon will catch that, and when it catches that muon, it'll change, that photon, it'll change its momentum accordingly. And that's what's happening. So imagine this is particle 1, that's particle 2, electron, muon, and the electron is throwing sort of a photon, and then they come back out. Right? So this is how the information is passed from one to the other, through the exchange of particles. Right? So the picture of interactions that we have. Okay. So the other thing that's important is that, so we talked about all these particles that we try to discover yesterday. So how do we make these things? Well, you guys all know about the equation equals mc squared, which says mass and energy are the same thing. So what that means is that if I can take a particle, right, it's got a certain amount of energy encapsulated in that mass of that particle, right? And so, so I can go and take that particle and speed it up, give it kinetic energy, right? So now that particle is holding both some energy that it has because of its mass and the kinetic energy because it's moving at some speed. And so then if I have a collision, it's possible that some of that kinetic energy that that particle had can convert it into mass of some other particle, basically. So what we do is we take particles low that, or like protons that we are comfortable with, give them a lot of kinetic energy, we collide them together, and to change some of that kinetic energy into energy that can be that would be captured in masses of higher energy particles. Okay? That's the basic principle. Okay. And so this is the same thing. For example, nuclear bombs and how they work is that there are different processes where when the nucleus is pulled together, basically, so I'm trying to explain this in a good way. So the nucleus has a certain binding energy, some energy for it to be able to bind together. To be able to pull something out of that nucleus, right, I need to actually hit it so it's holding on to the protons that are there. I need to pull that proton away, right? So to put energy into it to pull that proton away. That energy actually is encapsulated in the mass of the thing. So there's not only just the mass of particles here, but the dynamic mass of the binding that has to do with the energy that's stored in this is actually encapsulated in the mass of this thing. So a nuclear bomb or things, the way you do is you basically exploit these by breaking the nuclei and releasing that energy, okay, or converting it to other particles. Okay. So then as we turn on the energy of our particles, well, as I was saying, we see smaller and smaller distances, and we start having more energy to make more particles, right? So not only am I probing smaller distances, now that energy, as I turn it up higher and higher, what I can do is actually use that energy to make new particles through these interactions. Now, in general, these heavy new particles that we make, they don't live very long. They will decay very quickly. And so we don't, so the heaviest of these particles, we don't even really see them. What we see is the byproducts of what they decay into. And in fact, the byproducts of what they decay into, many of those will also decay. But they decay slower, and they're going fast enough so that they will decay after they've gone through a detector. So what happens is that I'll collide something together, I'll make a Higgs boson or something. That Higgs boson or top quark immediately decays to the particles it decays to. So it could be 2 photons, for example, for the Higgs, or it could be some quarks and leptons for the top. And those particles, the secondary particles, live long enough to go through our detector, and then they interact with our detector and leave imprint there, and then we know they were there. Okay? And then we'll infer the existence of those particles by going backwards. I see the byproducts and try to combine them together to see if I combine these things together, is it consistent with coming from a particle? And then if that's true, then I can say that particle was there in that event, or that, and if I can do that enough times, I can say that particle exists. Okay. So yeah, so they decay pretty quickly. So what we can, so they don't, these particles, most of them don't appear naturally, right, because they have decay. But what we do is we produce them in these collisions, and then see them decay. So then, let's see, what else? Now the other point is that we actually make, there's thousands of particles that we could make, and these things get routinely made, all these things. But there are only just a few of those particles that are fundamental. All those different particles that we can make are basically taking the quarks and sticking them together in different combinations in different ways. Most of those particles, those are most of the thousands of particles. Fundamentally, there's really the 6 quarks only and the 6 leptons only. Okay? So everything, all the other particles that we talk about are actually composite particles. Okay? And then the way that I can see these things is that, so for example, this could be a Z boson. So a Z boson. A Z boson, I've made it in a collision, and then that decays very quickly into 2 electrons. And what I see is the electrons, because those live and they don't decay, going through my detector. And I'll make a measurement of the trajectory of those electrons and the energy of those electrons, so I know that, the kinematics of those electrons. And what I'll do is, I know because of energy momentum conservation, if there's a particle of certain mass and it decay, there's a relationship between the mass and momentum of the initial particle and the mass and momentum of the final particles. It's just energy momentum conservation. If you think back at when we did basic mechanics, it's a billiard ball problem, right? Initial and final, the energy momentum is conserved, right? So I started 2 electrons, so I know the final state. I'll add them up together, and then I'll get the initial state. So I'll do an operation which adds what's called the 4 vectors, which is the momenta, which has 3 spatial components, and the mass of the object. I add those 2 together using the right formula, and it will give me as the 4 vector of the parent particle, which in this case would be this particle called the Z boson. And then what I can do is I can plot the mass of that that I compute when I did this. And if I plot the mass of that, what will happen is that, well, if it was random electrons and it wasn't really real electrons, what will happen is that it wouldn't peak. There wasn't a particle of a certain mass, right? So when I do those combinations, I'll get basically any kind of mass I can get because they were just randomly distributed. It just happened, there was some electron came from other sources. They're not correlated to each other. So I'll get some arbitrary mass. But if it came from a Z, the mass that I would get back would be close to the actual Z mass, right? And so if I look at a data set where I had lots of different collisions, and each collision I got electrons and added them together, and I calculated the mass, if I just histogram the mass, which means that every time I see a particular mass, so here is, I calculated the mass, my mass, let's say, could be between 60 and 160 GeV, just because that's my scale here. And what I do is I do this, get the 2 electrons, add them together, get the mass, and we'll see what the value of mass is. Oh, it's 80, and I put a bump here. And I'll do that to all of the candidates. What I'll see is that if in my data set there's a Z boson, I should see a peak. And this is how we do discovery. This is how we did the Higgs, except with 2 photons. Now the Higgs is really the problem there is that these end up being very clean, and particularly in this example. But the Higgs, going to 2 photons, there's lots of different sources of photons and ways that other things can fake photons. So the background is very, very large. So you just sit there and take a lot of data, and eventually that peak starts coming out. Okay? So this is how we know a particle exists. I didn't see the particle. What I saw was the fact that the byproducts of whatever I see in the detector, if I combine them together, are consistent with coming from a particle of a particular mass. Okay? That's how I know a particle is there. I didn't directly see the particle. All right, so then talk about HEP experiments in general, and some of you have seen this. Really, HEP experiments, then, what I need to do is I want to probe matter at very, very small scales and answer deep questions about those things. So I need to first get to high energies, right? So I need some sort of way of getting to high energies. So typically, that's a collider, right? And there are different types of colliders, and we can go through those at some point when it's appropriate, right? So I have a source of high energy collisions, okay? And then I have a detector, which is a big camera that I put around those collisions. So take a picture of the byproducts that come through, okay? So what I do is I turn on the beam and keep colliding particles together, and I keep taking pictures of those. And then I'll go through and find all those collisions that have 2 electrons together, and I'll add up the electrons in the right way and see a peak, and I say, aha, I see the Z. I made a Z boson. Okay? That's how it works. Now, detectors actually are typically made out of several subdetectors because each sort of different particles that live long enough to go through our detector so we can detect them, they have different types of interactions. So I'll talk to you a little bit about that. So this here, there's actually an interesting picture. So this is a picture of, for example, what could happen at a Large Hadron Collider when two protons will collide against each other. And those two protons can make two top quarks. And those top quarks will decay. And the top mostly decays to a W boson and a B quark. A B quark will turn into a jet because it doesn't. Quarks don't like to be alone; they always like to be with somebody else. So what they'll do is they'll actually it's more energetically favorable to create new particles from a vacuum to stick to it than to have this guy alone. So they'll turn into a spray of particles, and then the W a lot of times decays into an electron and an electron neutrino. An electron you can see, but electron neutrinos don't have any electromagnetic charge. So they'll just go straight to our detector and don't interact with anything, and we don't see it. So what you see is nothing in your detector due to those. So you see, and if there's energy momentum, the energy momentum should be conserved. What you'll see an event that is lopsided. All the energy is one side because there was a neutrino that went over there that you didn't see. But you can infer because of energy momentum conservation that there was a neutrino there and what the energy of the neutrino was at some level. Okay? That's what we do. So the machine, there are lots of different machines, but the big one is the LHC. This is a machine that's 27 kilometers, it's about 17 miles, it's about 100 meters on the ground. The machine was actually, the tunnel was actually built for a different accelerator called LEP, the Large Electron Positron Collider, so it's electron positrons that are collided together. When the SSC got canceled, which was this big 40 TeV collider that was going to be built in Waxahachie over here, and there's a reason that this school and many of the schools around here have strong high energy physics departments because people came in the early 90s here to do that, but it got canceled in 93. When that was canceled, the people at CERN said, well, maybe we can do it with our existing tunnels. So they came up with a plan of ripping out the existing electron-positron collider and putting a proton-proton collider in there. Okay? And we'll talk more about that collider and the technologies and those type of things later. But just so you know, that's the history of it. And it started taking data in about 2009, and we discovered the Higgs in 2012. Okay? Now, the way that the machine works is that you get protons going one way and the other way. And so they go like this, and then at certain points in the machine, you bring those two beams together and they collide against each other. Those points are called interaction points, and there's 4 interaction points on this accelerator, and each of them, around each of those interaction points, there's one detector. There's 2 big general-purpose detectors that are made for doing all types of physics. One is the ATLAS detector, which is the experiment I work on. The other one is the CMS detector, which is a competing experiment with very similar type of things, but shows different technologies for detection in some cases than we did. Okay? But each of them has some strengths and weaknesses. Each of those collaborations has 3,000 people in it. There's 2 other experiments also, one that does B physics, and another one that does heavy ion collision physics, which we're not going to talk too much about. Okay? Now, the machine actually, what happens is that you don't fill protons one by one that go through. What you do is you fill it up with lots of protons, and the protons are filled in something called bunches. So there's a bunch of protons. That means that there's a lot of protons pulled together. Okay, and then so you hit the machine holds 2,835 bunches. That's the design. So you have a bunch of protons. You have some space. You have another bunch of protons. You have space. Okay, and you have that both going this way and that way, bunches. And then what you're doing is actually bringing those bunches together. And so for you to get collisions, what you need to do is to make those squeeze those bunches as much as possible so that you have as much overlap between those 2 bunches when they collide against each other, so you can get the protons collide each other, so you get more collisions, so you can get more of whatever particle you want to make be built. Okay? Each one of those bunches has about 10 to 11 protons. Okay? And what's happening with LHC is that when you start the machine, you don't have very good what's called luminosity, have the amount of collisions that you get every time you cross. But as you get better, you tune the machine, you understand the machine, you squeeze these things down, you put more protons into it, you get more bunches into it, and you get to go to a higher and higher luminosity. And we just sort of in the past couple of years, about this run, I think we got the design before, but certainly now we're running at the design luminosity of the LHC. And then we're going to go beyond that design velocity, but because we'll get better. And then we'll shut down. There'll be an upgrade to the machine, which puts more stuff in it to be able to handle, better more protons in each bunch, more bunches, and squeeze the bunches more. And then we'll come back and we'll take data and we have more collisions and a higher rate. And then we'll shut down. There'll be one big shutdown. And in 2025 we'll come back and then we'll have a factor of 100 times more data coming out because we'll do a big upgrade to the machine. Okay? So that's the machine. The core of the machine are these superconducting magnets. They're about 25 meters long. They are superconductors that are kept in like 2 degrees Kelvin, and there's about 1,300 of these. CERN has the biggest cryogenics system anywhere. It's the biggest machine in the world, and the machine inside of it is all cooled down to very, very low temperatures. The reason you need the magnets is because we have an energetic particle. You want to turn and go around the accelerator, right, and the beam pipe. So you need to have magnets to do that. And the more energetic the particle, the stronger the magnetic field to get it to turn. Okay. All right. So the magnet's actually a key thing there. There's more pictures of the magnets and such. All right. So then, how do we see detectors? How do we see particles? There are 2 ways that we see particles, and I will go through these in great detail, but I just want to get you guys a picture of this right now. One is that when we do collision, one is that charged particles, when they go through material, they ionize material. And we know how to do that. We know the processes for all that stuff. It's very well understood. But what they do is, as they're going through, they'll bounce off stuff, and they'll leave a little bit of energy. They'll kick out the electrons, lose a little bit of energy in doing so. And if you can actually then collect those electrons that are kicked out before they get combined back into with where they came from, then you can actually know that there was a particle there. So a lot of our detectors, what they do is really just are trying to see this ionization in different ways. Okay? And we'll talk about detector technologies that do that. But one of those detector technologies is silicon, the same technology that goes into your cameras and your phones. And so basically, when the charged particle goes through one of those pixels, it will ionize that pixel, and then you can then just read out that pixel and say, there was an ion. That something went through. Okay? So the tracking detectors are actually the closest ones to the beam. They are all made of silicon, very, very high resolution, and they can very finely determine the positions that particles have interacted as they went through our detector. And then from that, we can do what's called pattern recognition, where I can see a pattern that hits, draw a line through it, and then fit that pattern, and then measure the curvature of that track. And what happens is that if you put that track, if you put those particles in a magnetic field, they'll bend, and how much they bend has to do with their momenta. So if you can measure that curvature, which is how much is bended, you get a measurement of the momenta. That's called tracking. Okay? And what's interesting is that, so when I was explaining to you these protons, bunches go by each other, every time they go by, it's not just one pair of protons that collide, there's 10 to 11 protons in there. There are multiple pairs. So when we started, there was just maybe 1 or 2 collisions. Now we're about up to 40, 50 collisions per crossing. And when we get to the upgrade, we're going to have 200 collisions per crossing. Okay? And you can actually see them by using a tracking detector. Here's one bunch crossing, and you can see all of these. So there's about area about this long, it's about 10 centimeters, I think this. You can see all the individual sort of collisions that happened and all the tracks that came out of those collisions. Okay? That's what that is. This is just showing the mean number of interactions per beam crossing. This beta that's here is for different tunes of how much you squeeze the beam, the bunches of the beam. The second way you can see particles is that if you put enough material in front of some particles, what they'll do is they'll shower. They'll break apart and lose energy and create secondary particles, would then create tertiary particles and so on. So it turns into a shower of particles. So basically, something comes in, hits, and disintegrates into a spray of particles. Okay? And I'll explain into the physics of this to you guys later, but what happens is that the number of secondary particles you get is proportional to the energy of the particle that came in. And so you just have to have a detector that some way can count those secondary particles. And I'll explain those things to you as we get to them. And then what you can do is you can basically build, a detector that's made of little blocks, and you instrument each block so you can see how much, you can count number of particles in each one of those blocks. A particle comes in and leaves some pattern of energy deposits because of the secondary and tertiary particles that went through here, and then you just see that, oh, this particular block was lit up with some energy, this brought out energy. And then I'll run algorithms will cluster those together and sum it all up and tell myself, aha, that was the energy of that one particle that came in. Okay? That's called calorimetry. And there's more details to this, there's lots of details to it, but I'm just, just want you to get a feel of it. So for example, if you take the calorimeter, so the detectors are cylindrical, right? Because you can have a collision, things go out, and you build things in concentric cylinders. If I unroll the calorimeter, it just looks like this. I just cut it and unrolled that toilet paper roll and just opened it up, right? And you can see where the particles went in that roll that way. So here, for example, you see there are 3 energy deposits in this one collision. Okay, that's what that is. And those are this, I think this. All right, so then detecting particles, and we'll go through these, and I'm actually expecting you guys to know things at this level. Each type of particle interacts differently. For example, a photon is not charged, but a photon, when it hits a calorimeter, will shower. So you'll see it, what's called an electromagnetic calorimeter, because it's the showering is due to interaction with the electrons and so on. An electron, it does have a charge, and it showers. So you'll see a track in the tracking detector, and you see a shower in the electromagnetic calorimeter. In fact, the shower looks very much like a photon. A muon is charged, but muons are kind of funny. They don't interact with anything, so they just minimally ionize everything. They don't ever shower. They just go through everything. In fact, the fundamental design constraint of LHC in terms of the differences between the two detectors is due to the fact that muons go through everything. So you need to have enough. Basically, if they're going really, really fast, you have to put them into enough magnetic field or have enough of a lever arm to be able to measure that curvature. So Atlas does it by building a huge detector so that you have a long lever arm, whereas CMS does it by having a really, really strong magnet, so you bend it more. Okay, those are the fundamental differences between the detector concepts is that actually. Okay. So then hadrons, which are things like pions and protons and those type of things, they are mostly charged, so they'll go through you'll see the tracking. They won't interact with the electromagnetic calorimeter because they're too heavy to punch through it, but they feel the strong force and they'll interact with the nuclei. So when they get to some very dense material, which is the type of calorimeter we call a hadronic calorimeter, they'll break up there and shower there. Okay? And then there's also neutrohadrons, then you will only see here, you won't see a track or anything. And then there's neutrinos, and neutrinos don't interact, so you don't see anything. And basically, the way you know it's there is because you saw everything else, and things don't balance out, so there must have been something that escaped. And you can, from that, you can infer some of the kinematics of that neutrino by measuring the kinematics of everything else, and adding it up and taking the minus. Okay? And yeah, so this is you can look at this picture. This is, for example, I guess this is a good picture of a muon that goes all the way through. Can't really see it too well. I guess this is an electron that's got a track and then showering. There's a proton that's got a track and is going in the hadronic calorimeter. Here's a neutron which doesn't have a track, but in the hadronic calorimeter. And here is, I guess this is the electron because it's a track, and this is a photon because it's not really a track, it's just a line neutron. So these pictures you can download the thing and see it nicely. But those are the concepts. And we will go through all these, actually. I will explain to you how these things work and why. At not too much detail level, but enough, because we're actually going to use images of these kind of interactions and classify them using deep neural networks. And what they're going to pick up is these kind of properties. So we should know a little bit about the stuff. We don't need to know the formulas in physics, so we should be able to look at them and understand what's going on. Okay. All right, so let's talk about our data. So an event kind of looks like this when you make it graphically, but that's not what you see, right? What we get is information. In fact, what we get is a list of, when the collisions happen, what happens is that particles spray through our detector, and then we have parts of the detector instrumented to measure energies or CCD kind of thing, measure that there was a charge there, whatever. There's millions of channels that will read out, which then we have to go through and turn into an image like this eventually. Okay. So let's talk about that step. First, talk about how much data there is, okay? So the back of envelope calculation, right, which physicists like to do, it's just rough calculation. There's about 100 million channels in atoms, okay? So I didn't say this, but when these protons, when I say the bunches go by, that happens 40 million times a second, okay? And each of the time that happens, you have 50 collisions. Right now, you'll have up to 200 in 10 years from now, okay? So that's to give you a sense, okay? 40 million times a second. Highly compressed, those 100 million channels, we can condense into 1.5 megabytes per collision, okay? So you just multiply that out, raw data, that's 60 terabytes of data a second. Okay? Now, this detector was actually built in the design in the 90s, and at that point, they only had gigabit fibers. So that's the technology that we rely on. And if you're going to calculate how many fibers you need to read 60 terabytes per second of data, you can do a rough calculation, and it's about, you need basically a fiber bundle with a radius of 2.5 meters. Okay? And the problem is that you have a detector that you want to measure everything. You want to know that, that neutrino missed because you saw everything else, right? But if you have a lot of cables coming out, there'll be areas that you can't instrument. It's cable, and then you'll miss it. So that doesn't work for us. We can't have so much cables coming out. So the point is that we can't actually read all that data. So what happens is that data gets collected and stored on electronics on the detector itself for about 2 microseconds of data. Okay? And what gets sent up actually at this point is an analog, because they didn't have the technology at that point, analog information about what they saw. So some of the detectors that they use, they read out the data both digital and analog. They'll send the data analog, and what they do is they'll take several channels and add them up together and send the data analog up to to some electronics in the back, which will be about 100 meters away in a different room. So racks and racks of electronics, which then try to, at very, very fast rates, try to, through electronics, be able to digitize it and then look for signatures of things that are interesting. Okay? Because what happens is that the physics that we're really interested in is actually rare. Most of the things that happen there are boring stuff that we know very, very well. There's about 1 in 10 to 11 collisions is something that we're looking for. So, and most of that stuff we can actually easily throw away because the things that we're looking for have a lot of unique signatures. If we're lucky to have a unique signature. So what we can do is we read off the detector really quickly through an analog and take a very coarse look to see, does it kind of look like it may have something interesting? And if it does, then we'd say read off the digital information off the detector. Okay? That's called a triggering system. That's our level 1 trigger in Atlas. Right? So we go from 40 megahertz to about 100 kilohertz that way. And then we'll go through software. We take that data and we combine it in different ways, and eventually we whittle that down through software processing of that data live, as we're taking data, down to a kilohertz. And that's what we write out today. So we went from 40 megahertz to a kilohertz. Okay? Yeah?
Do you know why every event is so large? 1.5 megabytes?
I mean, if you just 100 million channels.
Okay.
Right?
Yeah.
And these things are bit, they're packed. Like, we use just the number of bits that we need that has to do with the resolution of the ADC that's converted to bits. So we try, it's not even, very, should be pretty efficient. Okay. All right. So, right. So it's 1,000 events per second that we're actually writing out, and what that amounts to is about 10 petabytes a month each of these experiments. So my experiment and the one across the ring, the two big ones, make about 10 petabytes of data a month, raw data coming out of the experiment. Okay? And so this is probably the biggest source of data that's out there. It wasn't in the past, I don't know, there's no difference. This picture is just showing something. So when you have collisions, the rate of, everything's probabilistic, so there is a certain, what's called cross-section, which corresponds to a rate that certain things will happen. So when I'm colliding things, I'll make W's at kilohertz rates at the design luminosity. And whereas when I come down to things like the Higgs and whatever, I'm making them a much less. So it's a millihertz. So every 10 seconds or so, I make a Higgs. okay, or so. And it all has to do with the physics, but what you should notice is that as this is the masses of the particles we're talking about, as you get heavier and heavier and heavier, typically the cross sections become lower and the rates of making them becomes less and less. Okay? And then you need to have more collisions to be able to see them. Okay? So that gives you a sense of that data. And then that data that comes off of the detector, 100 hertz, these are just raw channels. What we have to do with those raw channels now is actually process them into some useful information, right? And so what we do is we go through something called reconstruction, which is algorithmically we'll go through the data and we'll try to find patterns and fit those patterns to things. And what you get out of reconstruction are, for every collision, a list of particle candidates. They say, look, if I look for electrons, it looks like these were the electrons. And if I look for muons, it looks like these were the muons. So you get a list of those. And the analysts then start with that list of those particles per event, and then start to look at them and say, well, this is not really an electron, but just, but this one really is, and I need a high energy electron for the particle that I'm looking for, and that kind of stuff. And they go through that sort of selection process on that data. Okay? So this thing called reconstruction is very important. Our reconstruction happens at a hertz level. Okay, just to get you a sense. All right? So you take it 1,000 hertz. But you get a hertz level, so you need lots of computers behind this to be able to keep up with the data coming in. And then that goes into sort of analysis. And typically, what you do is when you do analysis is that I'll start with a very sort of loose selection because I don't want to pick anything. So I'll look like, well, I know my final set has 2 electrons, so I'm going to always look for just stored events that have 2 electrons. But after that, I'm like, okay, well, I know that electrons have to be energetic, so let's just cut out the ones that are not very energetic, get the most energetic ones. And then other properties, and I've looked at this parameter already, and I've made the selection on it. I don't need it. I can get rid of this. So what you do is you take the data, which was started at 10 petabytes, you squeeze it into reconstruction as some other some other size. I have to figure out what that is, but it's hundreds of terabytes. Then you go and take that hundreds of terabytes of data. You go and you take a subset of it that's interesting, and that might be tens of terabytes. And then you go through that and you whittle it down, and you pull out the subset of interesting events and information that you need to be able to do the analysis, and take it down to maybe a terabyte or so, and then you start doing your analysis maybe on your laptop, on your home machine, to do the final things. So this sort of process of derivations. The other thing I would say that these systems have, the computing is completely distributed. No single place who has enough money to be able to do all the computing necessary. And at any given time, Atlas Collaboration is using about 300,000 cores around the world. And we process about 1 million jobs, move several petabytes of data every single day. So just to give you a sense. And so we do that by having this hierarchical, what's called the grid, and we have a grid site here at UTA. If you go to CBB and downstairs, you see there's a room full of machines, and that's what they're doing this stuff. I don't want to go too much. So let's just come back to why was it that HEP is a good thing for doing work with deep learning and all that stuff. We have the world's largest data sets, and we regularly apply and develop data science techniques. In fact, a lot of the techniques came from us. A lot of the initial data scientists and the tools that are out there actually came from our field because we were the original big data. We've been doing this for decades. Okay? And so we are, just because we had to do what we had to do, we're very well versed also in the data engineering part. I have to handle this data, so I have to figure out how to do this. I learned that stuff because I have to know it to do what I need to do. We build models. The physics itself is a model, right? But those models are sort of based on fundamental principles. The models we're talking about here will be empirical models. I don't understand fundamentally the physics of what's going on. I just want to be able to get something that will be able to do something for me. So they're more empirical. And we have some really hard problems, actually. One is that when we go to that upgrade 10 years from now with 100 times more data, we're worried actually don't have enough computing. If you do the calculation of how much computing you need, and count for Moore's law, which is pretty much dead, but you can say it's not dead, you compute how much energy, how much money we would need. We'll need 5 times as much money as we're spending today to really keep up with the data. And that's in the best case scenario. So we have to find some better way of doing things. Okay? And some other experiments, for example, there are algorithms that we don't know how to write the algorithm, but a human eye does better than algorithms. right? So these are problems. This is why we want to use deep learning, to be able to do these more efficiently, faster, or better than what we can code up. Okay? There's other reasons. Let's talk about deep learning. Oh man, I hope this is So, as I said, this is a biologically inspired computation. So the typical thing is you do sort of something called probabilistic inference. So you say, I got pictures, and then tell me which ones have dogs in them, which ones have cats in them. So that's the sort of typical application. And what we do in particle physics, I'm looking for this supersymmetric particle, and it's got all these backgrounds. So I train a neural network to be able to identify those supersymmetric particles above the backgrounds. That's what I do. There's an important theorem called the universal computation theorem for neural networks. It says that under certain conditions, neural networks can encapsulate any function, any high-dimensional function a neural network can encapsulate. Okay? Which is so these are sort of the two ways that we can sort of think about neural networks, so doing sort of classification tasks, those type of things. But also they can take any function, anything that's out there, and encapsulate it somehow. Okay. This deep neural networks is not a new idea. It's been there since at least '65. It's just impractical because something called the vanishing gradient problem, which basically means, and I'm not going to get time to get on that, but there are slides there, which I'll go through the next time. Basically, when you do the training of the networks, you have to do a minimization. You do a minimization by taking gradients of a function. And what happens is that the layers, each layer has an activation function. And what happens is that if the cost function is here, but you want to change this, figure out how much you should change this parameter, you have to take a derivative. You have to go through you apply a chain rule and go through all these and go through all those activation functions. And when you do that, by the time you get here, that derivative is extremely small. So then that means that when you take minimization, and walking on that gradient, you don't move those weights very much, so you can't train the already layers. The way that solved this problem was in three ways. One was they got smarter about the activations and how to do this kind of stuff in procedures. Two, well, it's small, but if you have enough data, you'll still eventually train the system. And three, if I need have all this data, I need actually the processing power to be able to do it, GPUs. So as I said, there's that trifecta. Okay? And so, there's sort of, there's been this, what we call this like deep learning renaissance in the past 10 years or so, where people have gotten, suddenly been able to train these networks and started doing really amazing feats like, image and audio and video recognition, captioning and text generation, those these crazy things. Even translation, all this stuff. The first paper in our field was actually for Dan Weitzen and them, and from 2014. It's actually something we're going to do in this class. It's a very rich field with a whole variety of architecture, techniques, and applications. Okay. The other interesting piece of the story, which you probably heard if you saw any of my talks, was that what got people's attention was that in 2012, what Google did was it took 1 million images from YouTube, 1 million videos from YouTube, took one frame, took a 200 by 200 pixel patch of that frame, and then used that to train a big neural network in an unsupervised way. Didn't tell it what's in the frame, they didn't even know. What it did was basically trained a neural network that says, I give you this input, reproduce that input. This is called the autoencoder, we'll talk about it in this class. And they did this, and they trained this on a $1 million cluster for a few weeks. And what they saw was that it just saw pixels, this thing. What they saw was that if they showed this thing a picture of a cat, it would have a certain response, and a dog would have a different response, and different objects have different response. So this thing had learned to be able to distinguish between cats and dogs and all these other type of objects, but then they were being told that there was actually a difference between them. So that you could then, use this to be able to make a classifier and identify things, which is interesting. That got people interested. The other one that was big was that DeepMind went and they took it's already a 2600 emulator. It's a gaming system from the 80s. You can run the emulator on any machine now. They took the pixels of those emulators, put it through a deep neural network, and the network could control the joystick, and it gets rewarded by whatever you get points in the game. And basically, that's all it needed. And then this thing learned to play something like 49 games, many of them better than a human being. After a few hours of time. Okay? So that's got people's attention. So there's actually links to all the stuff if you want to see over here, if you download the things, the links are actually there. The other thing that happened was that these image classification sort of competitions, they just got better and better and better until right now we're in a place where they do better than human beings. Okay, these things. So these are examples. I kind of showed these before, so I'm not going to say too much.